Once again, thank you very much. Thank you very much for coming. It is a late hour, so I appreciate your commitment. I hope this commitment will survive until the end of the semester. Right. So before we go on with the complex numbers, one extra announcement. It turned out that the schedule of questions for the tutorial, for the algebra tutorials which are printed in the yellow book which you obtained through the bookshop, is not correct. I presume most of you saw the announcement on Moodle. You need to make the adjustment. The correct schedule of questions, it's sitting on Moodle as a separate file. It is also given in the course handout. It's only one incorrect copy of it. It's only one incorrect copy of the schedule. It is in your yellow book, so be careful. All other copies on Moodle and in the course handout, they are correct one, and you need to use them. Okay, so last time we discovered with you two different ways how we can manipulate with complex numbers: Cartesian way and trigonometric or / exponential way. I'll show you a few examples today where interplay between these two different ways of manipulating of complex numbers delivers interesting results. The first one, it's a slide which I call perfect pentagon. It has some relation to perfect pentagon. I'm not sure if we reach that stage, but it starts with complex numbers. So the question itself, which I'd like to address with you, is this one: how to express a cos or sine, a trigonometric function of a multiple of an argument. Like, here's a typical example: cos of 5 theta. This is a Greek letter theta, in terms of cos and sine of 1 theta, or cos and sine of 1 theta. You from high school, you know some formulas of this type. For instance, you know the formula for the double angle. I hope you know the formula for the double angle. You know this formula that you know the formula that the sine of double theta equal to sine theta cos theta. That's the formula you know from high school. You know a similar formula for the cos of double angle, which is cos. You gotta be kidding. Sorry. Apologies. Looks like a number plate, doesn't it? Once again, so you also know from the high school the formula for double cos, which is cos square theta take sine square theta. Today I'll show you, the way how to come up with such formula for any multiple. I'll use the example of multiple 5 because it has some links with the perfect pentagon and the way we construct perfect pentagon. That's why the 5, and 5 actually it's a very interesting number. I mean, for instance, if I say 4, for the number 4, you can probably combine the double formula a few times and you come up with the formula for the cos of 4 theta or sine of 4 theta. But for the number 5, it's not so obvious. And complex numbers, in fact, gives you a uniform method how to deal with any problem of this type. So everything starts with the De Moivre theorem, the one we discussed with you on Thursday, this theorem. On Thursday, we saw this result. If you take a unit of complex number in trigonometric form and you raise it to some power, this is as good as if you just multiply the argument of this complex number by the same multiple, and that would be the basis of the whole method. Because what I will do now, I will just make the expansion on the left-hand side, and then I will equate the real and imaginary parts on the left-hand side and on the right-hand side separately. And that will give me the formula for the cos of 5 theta in terms of something on the left-hand side, which will be a combination of cos and sine of 1 theta, and for the imaginary part, sine of 5 theta will be equal to the imaginary part on the left-hand side, which is another combination of sine and cos of just one theta with no multiple. For the expansion here, it's a binomial formula again. For lower binomial formula, sorry, you have just remember what the expansion is for the square, for the cube. For the higher ones, we do the procedure which is called the Pascal triangle. If you don't know what that is about, I put the video and comments on Moodle last week concerning binomial formula and how we do the expansions for the higher powers. You can also Google that. There are plenty of material freely available on the net. How to do the binomial expansion. For the fifth one, all I do, I build the Pascal triangle. So what I do is this. That's how I build the Pascal triangle. You just start with number 1. You just write down another 2 number 1s underneath in the shape of a triangle, and then you start building your triangle like so. You put 1 and 1 on the sides, and in the middle you put a number which is equal to the 2 numbers above it. So for instance, in this middle I'll put the number 2, which is sum of these two, 1 and 1. And that's the second level of my Pascal triangle. And as a byproduct, the second level delivers the coefficients of the expansion for the square. If you remember, expansion for the square, it's 1, 2, 1. Again, I put 1 and 1. I put 1 and 1 on the sides, and in the middle I put the numbers. I put a number which is the sum of 2 numbers above it. So here will be 3. The sum of these 2 numbers above it will be another 3, and the number, the one at the back, I mean the last one, will be just another 1. That's the third level of my Pascal triangle. We build this up to the level 5 because we need the expansion for level 5. So it's a level 4, 1, 4, 6. By symmetry here will be 4 and 1. I'll no longer write this. And the fifth level is 1, 5, 10, and by symmetry will be 10, 5, and 1. Let me just write this. Probably I should write this. 10, 5, and 1. This is the fifth level of my Pascal triangle, and that's the coefficients of binomial expansion for the level, for the power 5. 4 and 1. That's what the Pascal triangle is, and that's how you build it. It's a step-by-step construction. Every next level, it's the numbers, which is sum of 2 numbers above it. Look at this. 4 is a sum of 3 and 1. 6 is a sum of 3 and 3. 10 is a sum of 4 and 6. This 10 is a sum of 6 and 4. This 5 is a sum of 4 and 1. And this level is exactly the coefficients of the expansion for the number 5. So if I want to see now, look back, if you just remember these coefficients, 1, 5, 10, 10, 5, 1, if I take these coefficients and I go back to my main side of the slide, if I want to see the expansion for the a plus b to the power of 5, all I need to do, I need to take these coefficients and spread them across the expansion like this. 1, 5, 10, 10, 5, and 1. Look at this. 1, 5, 10, 10, 5, and 1. It's a very powerful way, very express way, very quick way to find the expansions for any binomial of any order, in fact. All you need to do, you need to build this Pascal triangle to a certain level. If it's the first time you see this, you can take present, like you can believe me at this stage, that the expansion for the degree 5 looks like this. And that later on, when you do your independent study, I strongly encourage you to visit that extended commentary on the binomial expansion, which is on the Moodle right now, video commentary. And also you can Google, Wikipedia, or just any other resources on the internet about the binomial formula. And there isn't that much to remember, in fact, just the Pascal triangle and how you copy these coefficients to the expansion. So having this expansion now, I'm back to my original question, how to express cos of 5 angle in terms of the cos of the of one angle. all I have to do now, I have to apply this binomial expansion to my left-hand side here, and then equate the real and imaginary part separately. That's what I'm about to do. Look at this. I'll first take the real part on the right-hand side, which is as simple as cos phi theta, and then I'm taking the expansion. I'm taking this expansion. I apply this expansion. I'm taking this expansion of the binomial formula, and I apply it to the left-hand side, but I'm going to apply this in a smart way. I'm not going to take this, I'm going to just take my cos and sine and replace it across this right-hand side. Just replace it across the right-hand side. Instead, I will, while replacing, I will choose only those terms which deliver the real part. Let's just try to predict which of the parts will deliver the real part. Well, the real part will come if you, after you sub in your cos or I sine, the real part will come if after replacement there won't be any I present in there, right? But the I will come from the B. I mean, because B will be I sine theta, so I will come from the B. The only way for I to disappear if you sub in something for B, if your B comes in even power, isn't it? Because I itself is just I square will be -1, I cube will be I4 will be 1, and you cycled up, I5 will be I again. So in a smart expansion, rather than just bluntly replacing A and B with the cos theta and I sine theta, rather than just doing that, I will just pick up only those terms which comes with the even power of B. That's all I need in order to find the real part of this expansion. So how many of those I have? One of them here, B comes with the even power, 0 power. One of them here, B comes with the second power. One of them here, B comes with the fourth power. 3 terms altogether. These are the terms which will constitute the real part of this expansion. The rest I can just discard. I no longer care about them. So here they are, all of these 3 terms. A5, remember, cos plays the role of A, so cos phi theta. This one we don't care about. Here, B square, it will make it I disappear. Well, not completely disappear. There will be some influence of this B square. It will be negative now, right? Because I square will be -1. So this term 10 cos cube for the A cube and sine square for theta. But you see the sign here is negative rather than positive because I square made it negative. And the final term in this expansion is the one which represents this one. 5 cos theta for A and B4. It's sine 4 theta. I here completely disappeared and has no bearings on this term because I4 is just 1. That's how you do the smart expansion or smart application of the binomial formula here, because you only care for the real part. Now, another instance of the same smart expansion, when you now take the imaginary part on the right-hand side, it's a sine 5 theta, and now, from this expansion, I will take those terms which comes with the odd power of B, because those terms will present some I, will contribute some I into the expansion, right? So now I take this term, where B comes with the power 1. Here we go, 5 cos 4 sine, just sine. Now I take this term, B cube, and in my B cube, I will be in cube, which is just -I. So here it is. That's why we got negative here again. And now I have this, and I5, I to the power 5, delivers sine 5 theta. And that's all there is to it, as a matter of fact. Only, look at this, 1, 2, 3, 4 lines you need to find the expansion for a sine of cos of multiple of angle in terms of cos and sine of single angle, one angle. And plus, of course, the Pascal triangle. All of these numbers, it turns out, they're just coming from the Pascal triangle. So as long as you know how to reconstruct the Pascal triangle to a level you need, you can easily come up with a formula like this on any occasion. You should appreciate how robust and how uniform this algorithm is. Everything comes, of course, from our knowledge. Very little knowledge, in fact. We only spent 2 lectures on complex numbers. Our knowledge of complex numbers from here for de Moivre theorem. Yeah, this is de Moivre theorem. I have a marking. Any questions? Now I promised you a link with the perfect pentagon. I'll take this question a bit further. I can, rather than just saying I need to express my cos of 5 theta or sine of 5 theta in terms of sine and cos, I can make it even more strict. I can say, let's just find the expression in pure sines. Let's just find the expression for sine 5 theta in pure sines theta. No cos is allowed anymore. For that, we will need some extra steps. So I'll just focus on sine alone. Cos, you can do it for cos as well if you wish, but I'd like to discuss just sine. So again, I'd like to see how can we express sine 5 theta in pure sines with no coses present. So I will start off from this line, of course. Now all I need to do, I need to get rid of this cos 4 and this cos 2 cos squared. This will be more or less like an ad hoc solution. We will just use what we know, what I call the basic trigonometric identity. It's the one which says that the sine square of any angle plus cos square of any angle equal 1. That's the one which I call basic trigonometric identity. I can use that to get rid of this cos 4 and this cos square. All I need to do, I need to replace this cos with the 1 take sine square. I need to replace cos 4 with, again, 1 take sine square, but with extra square, which if you expand it via binomial will have this expression. So again, I will do a smart substitution now. I will track carefully everything what appears. I'm replacing this cos 4 and this cos square with the bracket like this and with the expansion like this. If I succeed in this step, the resulting expression will only have sines and there won't be any coses. So let's just try to do that. Let's just try to do that. If you make like if you look a little further forward before you even start writing anything into this expression, look at this. Just imagine you did the replacement. You replaced this cos 4 with this expansion and this cos square with this expansion. And then you did the extra expansions. If you multiply this sine across these terms and this sine cube across these terms, if we do all this, we will end up with lots of terms, but each of them will be either sine to the power 5 or sine to the power cube or just sine. Right? Because look at this. This sine theta, if you take it across this expansion, will be sine theta here, sine cube here, and sine phi here. This sine cube taken across this bracket will be sine cube and sine 5, and it's just sine 5. So altogether, there will be multiple terms, but in principle, there will be only 3 types of terms: sine phi, sine cube, and just sine. As soon as I realize that, I can do the smart expansion again. I will just write up these principal terms, and I just collect all of the coefficients I need. Look at this. All of my principal terms, sine phi, sine cube, sine, and here I combine all of the coefficients which appear in front of these sines in different positions. Look at this. This sine times this sine 4, that's one presentation of sine phi with the coefficient 5. That's why 5 came down here. This sine cube times this sine square, it's another sine to the power 5, and the coefficient is negative 10 plus another negative plus 10. Yeah, that's right. That's a plus 10 here. I was looking at a different place. And finally, sine 5 is from here. That's another plus 1. So combined coefficient of all appearances of sine 5 is 5, 10, and 1, which is 16. For the cube, similar analysis. Sine cube appears how many times? It appears once here when you take this sine with this double sine square, and the combined coefficient is negative 2 and 5. It's negative 10. And another negative 10 comes in here from this sine cube. and the linear sign with no power comes only once when this sign is multiplied by this 1. So the coefficient is 5. This is 5. So here's my presentation, or here's my representation, sorry, of sine 5 theta in terms of pure sine of single theta. Any questions? Okay, well, the original task which we had, the task was how to express sine of multiple angle in terms of sine of the single angle. We've done this task even with the extra requirement. We also done this task. Now I'm going to use this task to answer one extra question. The question is this: how to find the sine of pi on 5? Pi on 5 in degrees, how much is it? How many degrees it is? 180 by 5. Is it 32, isn't it? Oh, 36. Oh, sorry, 36. That's right. It is 36. So this, with the help of what we've done, we can add one extra angle to the sine and cos values we know from the top of our heads. How many other angles we know? We know 0, trivial angle. We know 30 degrees, which is pi on 6. We know 45 degrees, which is pi on 4. We know 60 degrees, which is pi on 3. We know 90 degrees. We also know the similar values in the other quadrants, but if you just focus on the first quadrant, that's all we know so far, 5 values. 2 of these are trivial, 0 and 90 degrees. With the help of what we just discovered, we can add one extra angle to this table, pi on 5, which is 36 degrees. And that's a big achievement. One day, some of you may learn that not many angles you can add to that table, to the table of sharply known values of sine and cos. So let's just try to do that. We're going to use this relation we just discovered with you. This relation of sine of 5 theta is this expression, because if you use pi on 5 value for theta, if you use that value for theta, and you call your sine, you're looking for unknown x, then you will end up with some sort of equation here. Here will be some expression in terms of your unknown x. On the right-hand side, on the left-hand side this way, the way it is written, it's the left-hand side. On the left-hand side, we will have sine of 5 times pi on 5, it's just pi. Sine of pi is 0. So we will have some sort of equation. Here it is. Here's the equation we will have if we use this value for x and this value for theta. Left-hand side of the equation came from here. Right-hand side of the equation came from the fact that sine of 5 times pi on 5 is just 0. Even though it looks like an equation of the 5th degree, it's the one we can solve exactly, right? I mean, we can easily factor out the trivial solution, x equals 0. And we will rule out the solution, because sine is not a 0 value. We know that for sure. It's some positive value. So this one, even though it's a solution, we disregard the solution. I factor out the solution. We end up with this what's this called? Biquadratic, isn't it? It's called biquadratic equation, because even though it is an equation of the degree 4, with the trivial substitution y equal x squared, you will end up with a quadratic equation for which you have the solution. Here it is. Here it is. If I use the formulae for the quadratic equation in place of this equation, that's what the formulae will deliver. These are the values for x squared. Yeah, that's right. These are the values for the x squared. So if I take a square root of this one, which one I should choose, plus or minus? Why? Why plus? Beg your pardon? So what? How do you see that the first quadrant ensures that we have to take plus? You don't have to do that. You don't have to say that. X squared is positive value, so of course this is supposed to be a positive value, but it is positive both for plus and minus. That's all fine. We all sometimes. So what do we choose, plus or minus? We cannot possibly have two different values for sine of pi and phi, for sine of 36 degrees. It's a single valued function. The value must be unique number. We don't have alternatives here. Huh? Guess and check. Okay, I know how to do guess. It's just a flip a coin kind of guess, right? Plus or minus. But how do you check? Well, the calculator will give you some discrepancy anyway. Well, how are you going to choose? For both values, there will be some approximation error. How are you going to choose which one is the correct value? Yes, please. Why do we need to get? Why do you think we will get such a value? I didn't catch that. Say again. If you take this value for theta, which is still in the first quadrant, it's a double of the first value, so it's 36 times 2, it's 72 degrees. It's still within the first quadrant. If you use this value for theta, the same logic works. If you take this value across this expression we come up with, left-hand side still will be 0. So if you take another x, so let me just call this x 1, and if I call this x2, which is a sine of 2 times, looks ugly, isn't it? Sine of 2 pi on 5. This value must also be the solution to my equation. So one of these values, I mean, after you take the square root of that, will be x1. The other value will be x2. But which one? Thanks to that comment, just give me, I'll let you speak in a second, thank you. Thanks to that comment, we now know that one of these values is with plus, one of them with minus, but how are we going to distinguish, please?
In the interval between 0 and pi on 2, sine is increasing.
That's another evidence, that's another knowledge of sine which help us to distinguish here. Thank you very much. Sine is increasing function, so for the larger angle, x2, the value must be larger. That's why the plus will go for x2 and minus go for x1. It's one of those examples where the choosing of a solution is subtle. You can't just say plus or minus. You have to employ deeper knowledge of the objects you study in order to make a distinction, and I'm very glad that you were able to make this distinction. But it's a very good example in this regard. So that's right. So x1, which is a sine of pi and phi we were looking for, is the one which comes with the minus, and x2, this extra value, it is the one which comes with the plus. So finally, the value we're going to add to the table we know is this value, sine pi and 5. The sharp value for this sine is like so. By implication, of course, you can also come up with a sharp value for the sine of double pi and 5, which will be the one with the plus. Yeah. Any questions? Now, finally, a few comments about the pentagon. Right. I don't know how many of you were ever heard about this part of the geometry which is called constructions of objects with the ruler and compass, but there is such an area in geometry where problems are all of this type. You only have two tools on your hands, a ruler with no marking on it, so a ruler which only allows you to draw straight lines but doesn't allow you to measure distances, and the compass which allows you to draw circles. And the tasks in this area of geometry is how to reconstruct different complex objects with these two tools, with the ruler with no markings and a compass. It's a quite exciting task actually. finding these algorithms or methods of reconstructing things. Normally you start with a simple task like how to split a segment in 2 equal halves, for instance. So if you picture a random segment on a piece of a paper, how to find a sharp middle point with these two tools. Do you know that? Does anyone know how to find a middle point? It's one of the basic sort of steps in building more complex algorithms, or how to, for instance, build up a perpendicular to a line through a point. I didn't catch that. Say again. Find the middle point of a segment. That's right. So it's like I said, it's an exciting part of the geometry, and the thing is, through history of mathematics, there were a few problems in this part which looked very complex and for a long time unsolvable. For instance, many of them were connected with the perfect pentagons. How to construct, for instance, a perfect equilateral triangle inscribed in a particular circle with a ruler and compass. This is a relatively easy task. Or perfect, what's this called? Sexagon, right? Yeah. Polygon with 6 angles. That's another one. Well, the pentagon stands out in this. in all of these tasks, constructing the pentagon stands out because it's one of those tasks which is on a level of difficulty. It's one level higher than all of the other polygons, triangle, polygon with 6 angles. You can't do 7, for instance. You can try, of course. It's long been attempted. Even ancient Greeks tried to attempt this, to reconstruct the polygon with perfect polygon with 7 vertices inscribed in a particular circle with a ruler and compass. Later on, it was discovered it's impossible with the tools available. But the pentagon, it's the one which you can do, even though the method of doing so, it's not that obvious. But what we discovered with you, it actually helps you to discover this method. And I'll just show you a few hints. Look at this. All you need to do to see this reconstruction is to modify this formula a little bit. Or in fact, let me just do it like this. Let me just zoom out a little bit. Here's the perfect pentagon. Here's a perfect pentagon, which is inscribed in a circle of radius 1. If you modify this formula a little bit, that's my modification. Look at this. If you modify this formula just a little bit, it's an extra modification. If you do the expansion within the square, and if you cancel things or make them simpler, there will be exactly this value under the square root. But this is a modification which helps you to reconstruct the algorithm for the perfect pentagon, because look what happens. Look what happens. If you have a circle of radius 1, and if you inscribe a perfect pentagon into that circle, the side of such pentagon will be exactly sine pi and 5, or double of sine pi and 5, right? Because the angle which facing one side of a pentagon, it's a 360 degrees divided by 5. It's a 72 degrees. The half of that angle, it's 36 degrees. That's the angle we know the sine for now. So in this right angle triangle, given that this hypotenuse is 1, the half of the side of the pentagon is sine pi and 5. And the complete side of a pentagon is the double of that sine. And for the double of that sine, we have now the formula of this type. With the help of this formula for the side of the pentagon, we can reconstruct the algorithm of building the pentagon with the ruler and compass. Look at this. All you do is this. You find the middle of this perpendicular diameter. There are a few steps which helps you to do that with the ruler and compass. Then this side will be 1/2. In this right angle triangle, the hypotenuse by Pythagoras is, what is it? The hypotenuse here by Pythagoras. Hey? Root 5 on 2. root 5 on 2. Now you take a compass, you put one leg of a compass in this point, you stretch it as far as this point, and then you drop the compass. You see I have this dashed blue circle representing this movement of a compass, and you mark a point here. Then this distance from the center of a circle to the point we just marked, what is it? Root 5 on 2, take 1. The whole radius of the circle we just, or the compass was the hypotenuse, which is root 5 on 2, and we subtracted this part, which is 1/2. So this bit now is exactly this bracket. Root 5 on 2, take 2. If you use the Pythagoras again, this is the one side of a triangle 1, this is another side of a triangle, which is this value. This red hypotenuse will be this root, big one, which is the side of my pentagon. So if I put a leg of my compass in this point now, and I open it as wide as this point, and I drag it and mark a point on my original circle, this stretch will be exactly the side of a perfect pentagon. This is the algorithm which comes directly from this formula and which allows you to reconstruct a perfect pentagon. The algorithm itself was known to ancient Greeks, by the way. They didn't know complex numbers. They didn't know binomial formula. They didn't know Pascal triangle, but they knew the algorithm we discovered through complex numbers. Just imagine how ingenious they were. Right, if you want to see the actual process of reconstructing in action, there's a video on the on my website on Moodle. There's a video. It's not my video. Actually, you can find plenty of videos of construction of the pentagon on YouTube. I chose one of them and I published this on the website. I will bring the link. I will bring this link once up when I do the video of this lecture. I suggest you look for it, and I suggest when you see that when the gentleman on that video does the construction, you try to track down this formula which appears in his constructions. I try to help you to see this, but in his construction, once again, try to see how these Pythagoras and roots, they reappear in his movements of ruler and compass. It's a nice task. And that's a link between the complex numbers and perfect pentagon. Any questions? Yes?
We need to know about the perfect pentagon. We need to know about this perfect pentagon.
You're very practical in this topic. You're always wondering what you need to know, what you don't need to know. It's not everything we do we need to know for the exam, right? I'm getting it. You need to know for the exam. Is that what you're asking?
Yeah.
Yes, you do need to know for the exam. Does it make your life easier? Well, if you split it in percentages, I spoke about perfect pentagon, maybe 10% of the whole presentation, and the rest was just complex numbers, right? So in terms of the percentages, you do need this for the exam, even though maybe perfect pentagon will not be there explicitly. Okay? Does it make your life easier? It doesn't, right? That's all right. Any other questions, please? Okay. Here's another topic I'd like to discuss with you. It's how we take roots of complex numbers. Basically, it all comes from the exponential form. I'll use this example of a tutorial book, 41, to show you what's happening. So the question in question 41 in the book, it says this: find the complex number such that you have the equation like so. If you make a simple substitution in here, and I suggest you do it because that shows you the structure of the equation. If you just introduce a new name, W, which is connected with the original Z by this reverse identity. If you make a simple substitution, then you will be looking at the equation W cubed equal negative 27. It's a canonical equation where you need to find a cubic root or root of some other degree of a complex number. The method of finding such a root is based on exponential forms. First, what you do is this. You convert everything to the exponential forms. For the w, you just choose this exponential form with the random letter, like just with the letters r and theta. And the cube then will take this form. W cube will be r cube e 3 theta. Let me just zoom in a little. 27, it's a little bit different. 27 we can convert to the exponential form with the exact numbers. So it's a negative real number, so the conversion is as good as this, as simple as this, sorry. 27 times -1 is split off the positive side. And you single out the unital factor, -1, and then here's your conversion. -1, one of the good choices for the exponential form of the -1 is ei pi, even though there are other choices as well. But ei pi seems like a good choice. So you write up your equation now in exponential form, left and right hand side. Here's a side for the w, here's a side for -27, and then you just equate radius to the radius and argument to the argument, but with the argument you remember we need to make the adjustment because the argument isn't something which is unique in terms of the for the complex number. So here's my I need to zoom out a little bit. This piece of the software a little bit buggy. So when I solve the first one, the r is 3 and the theta is pi and 3, right? If I equate this r of the real part, of the modulus to the modulus here, argument 3 theta to pi is one of the solutions. Like I said, because your argument is not unique, for 27 you can also come up with the alternative presentation. When you add up extra 2 pi to the argument, it doesn't change the complex number. So rather than taking this exponential for the -1, you can take this exponential for the -1. And when you start equating r and theta with this choice for the -1, you will come up with a different solution. For the theta, r will be the same, but the theta will be different. And still there is another choice for the -1. And still there's another choice for the -1. When you throw in, this time I actually subtracted -2 pi, you see? Rather than adding another 2 pi, I subtracted 2 pi from this pi. And by equating absolute value in the argument, you will end up with another value for theta, -0.3. Yeah, that's right, -0.3. So you see, by solving this equation for w or for r and theta, and by playing with the choice for the argument, we come up with the 3 different solutions already. If I keep playing this game, and I kept playing this game on my slide, I chose another I just introduced 4 pi now. In this case, my theta computations, here they are. And you see what happens? For this 4th choice of the argument, we ended up with a different value for theta, but this time this different value of theta, it is exactly by the step 2 pi from one of those we have discovered already. And that's something which actually a systematic thing which appears when you go for the roots of the complex numbers. By playing this game, this game, when you introduce the terms which are multiple of 2 pi, you will come up with the different values for the angle, for the theta, for the argument of your solution. But you will never come up more than 3 if you're taking the cubic root, or more than n if you're taking the nth root, different arguments. After you found all of the all of the n, any other angle or any other argument will be one of these n's. This is a fundamental fact about the roots of complex numbers, which you need to remember. This is a fact which I stress here as a theorem. If you solve an equation like this for z, you see root of n power from exponential I alpha, where n is an integer, that's important. All of the solutions will have the form like this. Where k takes one of these possible integers between 0 and n take 1. Altogether, n different values. That is exactly what we discovered here with the cubic root. We found 3 different values. Each of them are away from each other by this factor, 2 pi and 3, by 120 degrees. And altogether, we have 3 different values. Geometrically, these values, because you see what happens, you're just altering this extra increment by different case. Geometrically, all this root, they will be pointing to the vertices of the perfect pentagon. In case of 3, they will be pointing to the vertices of the perfect triangle or equilateral triangle. Here I have a picture for you. And I kept it to the scale. So this blue vector, that's the one which represents negative 27. The solutions to this, they will have the length 3 rather than 27. So my blue vector 9 times longer than the solutions. That's why I need such a scale. Here they are, all of the solutions. They point to the vertices of the equilateral triangle. This is the solution. This solution for the argument pi and 3. I call it W1 solution. This is W2, and this is W3 solution. This is something you will expect every time when you go for the root of a complex number. They will be spread out equally on the circumference of a unital, or not necessarily unital, depending on the modulus of your complex number, but on the circumference of a circle which is centered at the origin. And that's how we find the roots. Well, original question 41 requires now to convert W back to Z's by introducing this extra 6 take I term. Yes, and I did this. Look at this. So my W1, this W1, that's the one which corresponds to the angle pi and 3. So in trigonometric form, that this number, if I replace cos and sine with the values for the cos and sine which we know, that's the value of W1 in the Cartesian form. It's a W3 value, this value, angle negative pi and 3, that's a W2 value, angle pi. These are the 3 solutions in Cartesian form for my equation. If you now move to if you now do a back substitution, if you now find Z, given that we know the value of W, so by adding extra 6I to these 3 values, the values for Z, here they are. Z1 is this. Oh, I hit Z3 again by mistake. Z2 is this, and Z3 is like so. And that's the end of the question. Like I said again, the main thing which you need to take out of the solution and keep with you until the exam, because many of you are worried what you need, what you don't need for the exam. Here's a hint for you. This result, that's something which you need for the exam. When you take the nth root of a complex number, you will always end up with the n different solutions, and they will have very nice, beautiful geometric structure. They will be spread out on the circumference of a circle of a certain radius, depending what the modulus of your root is. Any questions? Okay, if you don't have any questions, thank you very much. It was a lovely lecture. Enjoy the second half today. Thank you. Thank you.